Hi guys, and welcome back to my channel. In this video and in this sort of series of videos, I'm going to be going over the Summer Chemistry Olympiad problems. So we'll go over the bronze and the silver problems. And the Summer Chemistry Olympiad is something that I found through the Chemistry Olympiad Discord server, or CODS. They host this and they administer this competition. And people from CODS have written these questions and been nice enough to share it with publish it so that I can sort of explain it and hopefully help you throughout your Chemistry Olympiad journey. So the bronze is supposed to be like the US SChO locals in terms of difficulty, but I found this problem 1, so we'll be going over problem 1 in this video. I found this to be a pretty difficult question and actually more difficult than almost a US SChO part 2. So this is not an easy question by any means, and let's just get right into it. So first, I want, if you're watching this video, take a minute or so to read through this first part of the question, and I'm just going to sort of skim through it and go through what I think is important to recognize. So take a minute and go through this, pause the video and go through this question. Okay, so I'll sort of read through it. We're looking at a binary compound, as it says there, and the compound has two elements, X and Y, so it's XNYM. And it says this compound has interesting applications. We're going to determine what the two elements are and then go over some reactions with this compound. So we're given two experiments. So these are the two important experiments we want to sort of look at. It says 1.2 grams of the compound was allowed to react with HCl. Gas evolved, so that's an important thing to note from the solution. So we know that there's a gas produced, and there's a remaining solid residue of 0.442 grams. Okay, and we see that through water displacement, the volume of the gas at SATP was 776.1 milliliters. Then it says when a lit match came near the collected gas, the gas ignited with a pop. So there's a bunch of clues in this experiment. Let's just go over the second experiment, and then we'll sort of talk about all the clues and what we want to recognize from these clues. Second experiment, 1.8 grams of the compound was allowed to react with NaOH this time, so it's a base reacting. Gas was evolved from the solution again. The reaction stopped. We have a remaining solid residue of 1.137 grams. So we still have a solid residue, different mass. Through water displacement, the volume of the gas at SATP was 1.176 liters. Once again, when the lit match came near the collected gas, the gas ignited with a pop. Okay, so we can see that there was a gas igniting with the pop each time. And if you've sort of done a chemistry lab class or something, or did like lab, have you had any lab experience? You would have heard of something called the pop test. And this is to detect hydrogen gas. So basically we know our gas is hydrogen. Another way to sort of think about this is, I'll explain a little bit later once we go over this one clue I wrote to the side. So later on in the question they give you a sort of extended clue to make the question a little bit easier and more bronze level, because without the clue it's actually quite a difficult question. So let's look at this clue and see how we can use that to inform us, right? So you may have noticed this already, but we will assume the different elements within the binary compound react with different reagents. So X reacts with HCl, Y reacts with NaOH. So this is kind of important. X reacts with the HCl, so X plus the HCl goes to something, Y plus the NaOH goes to something. So basically we're saying that X reacts with HCl. And if we look at this compound, right, if we look at XNYM, we can see X might resemble something like a cation, right? Or X might resemble a metal, more importantly, right? So metals sort of kind of react with acid to form hydrogen gas, which is another way you might have deciphered that hydrogen gas was the gas that was produced. But either way you figure this out, whether the pop test or looking at metals reacting with acids, you should find that hydrogen gas is the gas produced, and that's actually the question of 1.3. So 1.3 is hydrogen gas. H2 gas is produced, and Y, basically pop test. And what this pop test is doing is when a lit match comes, so I'm basically burning it, right? When you burn something, you're reacting it with oxygen. So when hydrogen reacts with oxygen, it forms water, and this sort of reaction causes a mini explosion, a little pop. So that's sort of your answer for 1.3. And now let's go over the other clues in the question, right? Okay, so we have solid residues happening in both experiments. Now, if we look at our clue, so this is where the clue comes in more importantly, is we say that X reacts with HCl, Y reacts with NaOH. So say in my first experiment, I'm reacting this compound with HCl, right? Only the X is going to be reacting. So what does that mean? That means the Y is basically left behind. The Y is not reacting, so the Y is the solid residue. The Y is what is left behind that hasn't reacted. And with experiment 2, right, the same thing is happening except with Y instead of X. So we have NaOH reacting with the compound, but remember, Y is the only thing that reacts with NaOH, so the X is the one that's left behind. So our solid residue is X. This is sort of going to be important, but that's another thing to note, and that's where this clue comes in really handy. I found it kind of difficult to just assume that without having this clue. Okay, so now let's look at the actual questions, right? Oh, and finally, below the experiments, it also tells you the vapor pressure of water at 25 degrees Celsius is 23.88 millimeter mercury. So that's another important number that we're going to use in our calculations. Now let's look at 1.1 and 1.2. Basically, this is asking us to determine the amount of gas formed in experiment 1 in moles. So what are we told about the gas? We're told that through water displacement, the volume of the gas at SATP. SATP gives us a certain temperature and a certain pressure, and we get the volume of the gas. So we have temperature, pressure, and volume. We can find the moles, right, through ideal gas law. So N equals PV over RT. And our pressure, right, but this is where we got to be careful, because our total pressure is coming from not only the hydrogen gas, but also the vapor pressure of water. So our total pressures are 1.013 atmospheres, but that's coming from not only the hydrogen gas, but the water as well. So basically we got to subtract off the pressure that comes from the water to calculate the moles of hydrogen gas. So our actual pressure, right, is our 1.013 atmospheres, but we want to multiply this by the conversion factor to millimeter mercury, which is 760 millimeter mercury per atmosphere. So that's the total pressure. Now we want to subtract off the 23.8 that's coming from the water. Our volume is 0.7761 liters, all divided by R, which R for millimeter mercury is 62.36, times our temperature, right? 25 degrees Celsius should be 298 Kelvin. Okay, so now we just got to plug this all into a calculator, and we should get that the amount of gas formed is around 0.03114 moles. So that was just ideal gas law. And now we can do the same exact thing, but for experiment 2, right? So what do we got to change? We just got to change a few numbers. So with experiment 2, right, we have the pressure, again, it's at SATP. So we have the same exact pressure of gas because we take the 1.013, convert that to millimeter mercury, subtract off the vapor pressure of water. But our volume of the gas is different, so we just got to change that. So let's change the volume of the gas. We can see that in experiment 2, the volume of the gas was 1.176 liters. So we just have to change that, and because it's at SATP, we know the temperature is still 25 degrees Celsius. So if we plug this all into our calculator, what do we get? We should get 0.04719 moles. Okay, so these questions were pretty relatively simple, right? We just had to use ideal gas law and then we had to look at the pop test and figure out the hydrogen gas was produced. But these were relatively simple questions. I think the next part of this question is relatively more difficult, and this is more where we need our hints a little bit. So let's go to the next part of the question, and I'll explain that. So again, this is the actual extended version of the hint. I'll just read it a little bit and sort of note the important things to take away. You may have noticed this already, but different elements, right, react with different reagents. X reacts with HCl, Y reacts with NaOH. So this is what we saw, what we looked at in our previous question, or in our previous part. The next thing is, because we don't know the subscripts of the elements, we should write a general reaction with the element as a reactant. So instead of dealing with the compound, let's deal with each element just reacting. So for example, when I write the expression, when I write the equation for X reacting with HCl, I just want to write X plus HCl rather than writing X M Y N or something like that, right? We want to keep this as simple as possible. So that's another hint. The next thing is something you may have noticed, is that depending on the oxidation state of the element in the product, the amount of gas released changes. So what does this sort of mean? Let's look at this with X reacting with HCl. So X plus HCl, say the oxidation state of the X was 4, right? Say it was 4 plus, right? So what does that mean? If it was 4 plus, that means this would form a salt XCl4, right? So we go from a 0 oxidation state to a +4, and then to balance this out, we would get 2 hydrogen gas. But say that our oxidation state was 2 plus, X plus HCl, then we would form the salt, but this would form the salt XCl2 because our oxidation state is +2. So we would need 2 HCl, and this would form 1 mole of H2. So we can see that if our oxidation state is 4 plus, we form more gas, 2 plus, slightly less gas, and as the oxidation state increases, we would form more gas, right? So that's just something to note. And then the last hint says, a useful technique you should try out is to write test cases where the element ends up in a +K oxidation state. So we want to say that instead of like taking 4 or 2 or some specific oxidation state, let's assume it has a +K oxidation state and work with sort of variables, and then test out these different variables at the end. So this is what we're going to do in this question, and how much gas would be released by balancing that chemical equation. Okay, so these are some good hints for this question and make it a little more manageable as a bronze problem. So let's go through exactly how you would write the equations and stuff like that. So, sorry, it's taking me a while to erase this. Okay, so let's do 1.4. Determine the reaction that occurs in experiment 1 and the identity of X. So this question will probably take a little bit of time. These questions are slightly more involved. So first we know that we're looking at a metal reacting with an acid, sort of like that. So we looked at it before, right, in the previous parts, and we sort of thought, okay, it's going to form hydrogen gas, and it's going to form some salt, right? So X plus HCl is going to form. Now we want it to end in an oxidation state of K+. We know that this ends in some salt XCl something, right? It's going to end in some salt with our metal, X, and our anion, which is going to be chlorine. Chlorine has the -1 oxidation state. So we're going to need K amounts of chlorine for X to have a +K oxidation state. It's going to have XClK, and we're going to have hydrogen gas formed. Now we just got to balance this expression, right? So we need K HCl's to balance the chlorines, and then we need K over 2 hydrogen gases to balance the hydrogens. So, okay, now we just wrote the reaction in experiment 1, but we got to figure out what X actually is, right? So let's look at our previous question, and we figured out something about the amount of moles of hydrogen, right, in our previous question, And we also figured something out. We know something about the mass of X. And how do we know all of these things? So first, let's go over what the amount of moles of hydrogen gas was. In the previous parts, we solved for the amount of moles of hydrogen gas released, and we got 0.03114 moles. That's how many moles of hydrogen gas was released. Okay, how do we know what the mass of X was? If you remember, right, we said that our compound, we said 1.2 grams of our compound, XNYM, reacted with acid, and it formed 0.442 grams, this is all in the previous part, of our solid residue. And we said that this solid residue was going to be Y, right? This is Y. It's the same thing as the element Y. Why is that, right? Because our Y is not reacting with the acid. The only thing reacting with the acid is the X part. So the Y is just going to be the same as before. It's just going to be the solid that it was. So our solid residue is just going to be Y. Okay, and we know that there was 1.2 grams of the entire compound to begin with. The entire compound is made up of X and Y. So if I take the amount of, if I take the total compound, 1.2 grams, subtract off the amount of Y, right, there was 0.442 grams of Y. What does this get me? This gets me 0.758 grams of X, right? So now I know how much, what was the mass of the X that was reacting, right? So it was 0.758 grams of X. Now what can I do, right? What sort of, how can I make a test case? How can I make test cases or sort of see what's reasonable for what X could be, and based on the amount of moles of hydrogen gas that was released, right? How can I write? So first I want to write sort of like a stoichiometric expression, right? So let's take our 0.758 grams of X. Now, if I wanted to find the amount of moles of X, I would divide by the molar mass, right? So I take this and I divide by the molar mass of X. And then if I wanted to find from the amount of moles of X, the amount of moles of hydrogen gas released, you can see that in our equation we have a 1 to K/2 ratio. So I got to multiply this by K/2, and this equals the amount of moles of H2, right? So now we have sort of an expression. Now what can we do, right? We can move this around a little bit. So say we move this around and we solve for the molar mass of X. How can we do that? 0.758 K/2 times NH2, right? I'm just rearranging this expression a little bit. What does this get us? This gets us molar mass of X. Okay, so what can we do now? We can try out a bunch of different Ks and see if any molar masses are reasonable, right? So let's do that. So if you plug in K equals 1, we'll get, for our molar mass, and remember the NH2 is 0.03114 moles, you plug in K equals 1, we'll get that the molar mass is around 12, which gets us an X equals C, carbon. If we do K equals 2, I'm just going to write out a bunch of test cases, and then we'll sort of go into what's reasonable. If we do K equals 2, we get that X equals something like magnesium. So basically, you just find the molar mass, and then look at the periodic table and see what corresponds to that. If we do K equals 3, we get X equals chlorine, right? So that's sort of, we're just looking through the test cases. Now let's use our chemical intuition a little bit and see what's actually reasonable. So if K equals 1, right, what does that mean at the end? At the end, that means carbon's reacting with acid to end up in a +1 oxidation state. So CCl. This really doesn't make any sense, right? That's not really a compound. Carbon doesn't want to lose an electron very much. It really never forms a +1 oxidation state. So this is not very reasonable. Now let's look at magnesium. If we have magnesium and K equals 2, that means that at the end, what are we forming? We're forming MgCl2. This is perfectly reasonable. In fact, this makes a lot of sense, right? Magnesium likes to lose 2 electrons to get the noble gas configuration. It's really stable as a 2+ cation. So this makes a lot of sense. Magnesium does react with acid. We know that. So some of this compound, yes, that makes a lot of sense. And at this point, we really don't have to go any further because this makes basically the most sense. If we look at the next one, just to go through it, if we look at chlorine, if chlorine and K equals 3, that means chlorine has a 3+ oxidation state. That really doesn't make any sense at all, again, right? We need something that's a cation, because if we look at the salt, that would mean we had like Cl3, Cl3, or just Cl4. That doesn't make any sense. So anyway, right? Chlorine doesn't make sense. Magnesium is the only one that makes sort of any sense. So we're going to say that X is magnesium. And now we want to write the entire reaction because it says determine the reaction. So let's just substitute X for magnesium. And K, now we know K is 2. So we should get Mg plus 2HCl goes to form MgCl2 and hydrogen gas. Okay, so now I want to talk about the reaction that occurs in experiment 2. And this is going to be really similar to what we did in experiment 1. And we're going to write the equation with Y really similarly as we did with X, except we're reacting with OH minus, we're reacting with a base rather than an acid. And we're going to still use this sort of variable of K to test out different elements and to keep everything organized, right? So let's do this on the next page. How is our reaction going to look? Let's sort of write our reaction out. So we're going to have Y, and we're going to react it with OH minus. I'm going to leave the the sodium cation out of the way because it's a spectator ion, and I just don't want to deal with it. So yeah, I'm going to leave it out of the expression. We know that there was also a pop sound, so H2 is formed with Y reacting with OH minus. Okay. So now what we want to find what else is formed. And this is where our Y is going to be in our plus K oxidation state, right? So we also know that all the oxygen has to be in this compound with the Y, right? Why is that so? Because the only other thing that's formed is our H2, our hydrogen gas. There's no oxygen in there. So all the mass, so we basically have to balance the atoms. All the oxygen needs to be in our compound with Y. And Y, think of it as sort of like an anion. It's like an anion oxidation. It's not actually exactly that, but it's similar to that. Like when we have chlorine getting oxidized, this can form ClO minus, ClO4 minus. It's like this sort of idea of oxidation. So that's how we're going to think of this. We're going to write this as YO. So how many, basically the question we want to ask is how many oxygens need to be there for Y to have a plus K state. And if we balance this all out, we get that there needs to be K oxygens. So I'll just explain why this is so. But this basically balances both the charge on both sides and the mass on both sides. That's our general idea as to why we picked K oxygens. So let me explain this first. We know that oxygen has a -2 oxidation state. So if we look at this, right, our K oxygens will have a -2K. In total, this anion has a minus K charge. So our Y must have a plus K, which is exactly what we want. We want Y to be in an oxidation state of plus K. The other thing you notice is that there is there's a minus K charge on the right side. So that means that there should be a minus K charge on the left side. Charge needs to be conserved. So, and we can see on the left side, right, we have K OH minuses, we have K hydroxides. Each hydroxide has 1 minus, so K of them is going to have a minus K charge. So we've balanced our charges. The other thing to look for is balancing our atoms. We can see that we haven't balanced hydrogen just yet, so let's balance hydrogen actually now. You can see that we have K hydrogens on the left side, So we need to have K hydrogens on the right side. So we need to have the coefficient of K over 2. Because this is hydrogen, the hydrogen molecule, not the hydrogen atom. And we can see for our oxygen, we have that balanced because we have KOs on the left side, we have KOs on the right side. Okay, so now that we've balanced our equation sort of well, we can go on to doing the actual math to figure out what Y is. So let's do that. We have this equation, and in the previous parts, we were given that we had a solid residue of 1.137 grams. That was our solid residue. And remember, just like our previous thing, when we have Y reacting with OH minus, the residue is just going to be the leftover X, because we didn't, that wasn't reacted. It's just going to stay in its solid form. So this residue is the same thing as our element X. And in this experiment, in experiment 2, it was given that 1.8 grams of the entire compound was reacted, right? So basically the mass of Y, if we look at the mass of Y, it must be 1.8 minus 1.137. If we plug this into our calculator, we get 0.663 grams of Y. Okay, so now we got to look at the so just like we did in the previous part, let's relate the grams of Y to the amount of the moles of hydrogen gas produced. If we remember, we calculated the moles of hydrogen gas that was produced, and we got some value. We got 0.04719 moles. Okay, so let's relate the grams of Y, the molar mass of Y, and to the moles of hydrogen gas produced. 0.663 grams Y divided by molar mass of Y, right? And then we have our stoichiometric ratio of K over 2 to 1, so times K over 2. This has to give us the amount of moles of hydrogen gas produced. And we can do the same sort of rearrangement we did last time to find that molar mass of Y equals our 0.663 grams of Y divided by 2 times NH2 times our K. So basically we did the same manipulation we did last time, and now let's look at different values of K and figure out what the element Y would be. So if K equals 1, what do we get? We get that Y equals lithium. So basically this means that at the end of the day, right, if Y was lithium, that means at the end of the day we form this LiO minus sort of anion, which really doesn't make any sense at all, right? This would really never form, right? Yeah, this is not a normal compound, and it really would not form at all. So basically this kind of makes no sense. Let's keep going. Let's say K equals 2. What does that mean? We have Y equals nitrogen, and what would this mean, right? If Y was nitrogen, let's look at what's produced. NO2, right, because K is 2, 2 minus. Again, this is not really stable. If we had NO2 minus, right, if we had nitrite, then maybe it would be it would be way more reasonable. But NO2 2 minus, that doesn't make sense at all. So we're going to sort of eliminate K equals 2 as well, and let's keep going. What happens if we do K equals 3? Y is, and when I'm just finding Y, basically what I'm doing is I'm plugging the K equals 3 into this molar mass equation, finding that molar mass, and then looking at the periodic table to find what element is close to that value. If K equals 3, we get Y equals neon or sort of sodium, but it's sort of in the middle of these two, right? So it's not really perfect. It's not a very good calculation. So, and neither of these would form a +3, because if we have K equals 3, that means we're ending in a +3 oxidation state, right? +3 oxidation state. Sodium would form a +1 oxidation state. Neon would be very unreactive. So that doesn't really make much sense, because neon's a noble gas. If we did K equals 4, we get Y equals silicon. And this is our first sort of more reasonable answer. If we look at our final product, that means we form SiO4 4-, which is pretty reasonable anion, right? You might have seen these sort of silicon anions before, and if you haven't, hopefully now you've seen them. But these silicon anions are they're way more stable. And it also makes sense because silicon, right? Silicon is very acid resistant. And in our first question, if you remember, we said that when the compound reacts with acid, only the X is reacting and the Y doesn't react. Remember, if silicon is Y, that means the silicon wouldn't react with acid, which makes sense. So let's keep this as our number one option so far. And let's just test one or two more. If we do K equals 5, we get Y equals chlorine. And if we look at the anion that would form, that means we formed a ClO5 5-. This is just too high of, this basically doesn't exist. This does not exist, or it's really rare. It doesn't make much sense as an ionic compound. We might have seen like chlorate or perchlorate or stuff like that before, ClO4-, ClO3-, stuff like that. But we never really see ClO5 5-. It's a little bit out there. So this is not a good option. So basically, we've looked at a bunch of these options, and we've seen that K equals 4 is the only sort of reasonable option for Y. And this turns out to be correct. We have Y equals silicon. So if we look back at our problem, right, the identity of Y is silicon. And if we want to write the reaction that occurs, how can we write the reaction that occurs? We can just substitute, if we look at this, we just want to substitute Y as silicon and K as 4. So let's just do that. Silicon plus 4OH-, right, forms SiO4 4-, so we can see charge is balanced, and to keep mass balanced, we want to do plus 2H2. Okay, cool. So that should make sense, right? And now we want to go to the next question. This is so 1.5 and 1.4 we just did. We wrote the reactions, and we found the identities of X and Y. The next question is determine the empirical formula of the binary compound. So how can we do this? Well, remember that we actually know in, say, if we look at the first experiment, 1.2 grams of our compound and 0.442 grams of solid residue. So let's look at that. 1.2 grams of our compound X, our compound is XNYM. We have this compound, and we have 0.442 grams of residue, and that residue is Y. So what does this mean? We can actually find the amount of X. So if we plug this into our calculator, 1.2 minus 0.442, because the masses need to add up, because X and Y are the only two things in this compound, this implies that we have 0.758 grams of X. And we know X is magnesium, Y is silicon, right? So now this just turns into a stoichiometry problem. Let's take the 0.442 grams of Y, divide this by the molar mass of silicon, right? And the 0.758 grams of X divided by the molar mass of magnesium. And look at the ratio between these two, right? This should give us the molar ratio, because this is the amount of moles of Y in this compound. This is the amount of moles of X in that compound. And based on that, we should be able to find the molar ratio. But basically, we can see that this implies 0.0157 moles of silicon. This implies 0.0312 moles of magnesium. And in the end, we can see that there's sort of like a 1-to-2 ratio. 1-to-2 is the thing for moles of silicon to, moles of silicon to moles of magnesium. So we have the empirical formula is Mg2Si. And that's the empirical formula of our compound. So we just solved this entire part of the question, and let me just write it down here, Mg2Si. So this was probably one of the hardest parts of this question, and I think the last part is equally a little bit challenging, but hopefully this gave you intuition of it's really useful to sort of take these variables. So in this case, we used k, and tried out a bunch of different values of k, try out a bunch of different things in a systematic manner, right? That's what's really good about stoichiometry problems. Usually you'll never find just one element. You need to look through a bunch of elements and see what's actually reasonable. And you want to do this in a sort of systematic and a easy to follow manner. You don't want to just randomly be finding different elements and just randomly testing them. So you can see here we looked, okay, k equals 1, what does this imply? K equals 2, what does that imply? K equals 3, what does that imply? And then we found an entire list and then said what is most reasonable, right? This is sort of the way you want to be thinking generally with stoichiometry problems. And these sort of questions come up a lot on USNCO Part 2s. But actually on those tests, on the Part 2s, they're actually, I would say, easier than this. But in camp, you'll get more difficult stoichiometry problems, and they'll be similar to this in that you have to take a variable and change that variable and see how that affects molar masses, and then see what elements are relevant, what elements make sense. Use your intuition. So hopefully this gave you an idea of how to approach problems like this. So now to the final question. Final question. When 1 gram of the compound was heated with concentrated hydrochloric acid, the outcome seemed different in comparison to the other experiments. It's different. Okay, so we got to throw our knowledge out the window about just X reacting and forming hydrogen gas and whatnot, right? Let's look at, there were visible sparks present and no gas was collected. There was no visible solid residue. Okay, so this is a lot of important information. Let's look through this. No visible solid residue. What did we say was the solid residue when we looked at the first 2 experiments? The solid residue was either X or Y, right? Or now that we know the elements, either Mg or silicon. What does it mean when there's no visible solid residue? That means that both of these guys reacted, not just one, right? When we had acid before, we had that magnesium was reacting, silicon just stayed silicon and was a solid. Now we see that there's no visible solid residue. That means that the silicon also had to react, because silicon by itself is just a solid. So what does this tell us? No visible solid residue. This tells us both magnesium and silicon reacted. That's the first thing we want to get out of it. What is the next thing? There were visible sparks present, no gas was collected. Okay, no gas collected. What does that mean? First of all, there can't be no H2 production, no hydrogen gas production. Because if there was hydrogen gas, then there would be gas, right? There would be gas that was collected. There are visible sparks. Again, this is not a sign of hydrogen gas, right? With hydrogen gas, it's only once you put a little lit flame that you get a little mini explosion. If there's visible sparks, we know that it's definitely not hydrogen gas. There's something else at play. So no hydrogen, both of these guys are reacting. Okay, so that's the 2 key important things we want to know when we're looking at how to predict these reactions. The next thing we see is that 1 gram of this compound was heated with concentrated hydrochloric acid in an inert atmosphere. The gas was collected, and when the gas was introduced to a 1 liter balloon filled with oxygen, the volume decreased by 58.4%. Okay, so this is a lot of information, but what do we want to get out of this? Basically, when we're heating this in an inert atmosphere, so there was a gas produced. It was because the atmosphere was not inert that it sort of like reacted, maybe, and no gas could be collected. But when there's an inert atmosphere, there is a gas produced. So there actually is gas production. So we do have gas production. It's just a really reactive gas that reacts with something in the atmosphere almost immediately, right? So there is gas production. Okay. And then the gas could be collected, and when the gas was introduced to some 1 liter balloon of oxygen at STP, the volume is decreasing. what does that mean when the volume is decreasing? That means this gas maybe reacts with oxygen. So it's basically sucking, if we introduce this gas into some volume of oxygen, it's reacting with this oxygen and maybe forms a solid or a liquid, right? So it's taking oxygen out of the balloon and reacting with it, right? It's reducing the amount of moles of gas in the balloon, and that's going to reduce the volume of the balloon because the pressure doesn't change. The pressure is going to equilibrate to atmospheric pressure. So we're basically sucking oxygen and sucking the gas out of the balloon and forming something that's not a gas. So these are all sort of important things. We know that the gas that's produced basically is reactive with oxygen. Okay, so what exactly, so this is kind of a tricky question, but we're going to figure out what 1.7 is. Determine the identity of this gas and the chemical equations of the reactions. Explain your reasoning. So we already know what happens when magnesium reacts with acid, right? We've already done that. Basically, what we're confused about is why is silicon reacting with acid and what is it forming? So let's just write Mg2Si, right? That's our compound. React this with HCl. We form MgCl2. And generally, right, this should be 2HCl. Before we had hydrogen gas being produced, but now we're not having hydrogen gas being produced. We're having something else be produced. And what else is being produced? Actually, I won't balance this equation just yet because we want to figure out what else is being produced. So we can see that our magnesium is sort of accounted for on the left and right side. We just have to balance this. But let's balance it at the end. Our magnesium is accounted for on the left and right side. Our chlorine is accounted for on the left and right side. Our hydrogen is not accounted for on the right side, and our silicon is not accounted for on the right side. So what does this mean? Silicon maybe formed a compound with the hydrogen, right? And if you think about, this is a gas as well, right? A gas was produced. MgCl2 is an ionic solid. So for a gas to be produced that's not hydrogen, maybe it's some silicon-hydrogen combination. If we think about silicon, we look at above it on the periodic table, right above it is carbon. So its sort of molecular compounds might be similar to that of carbon. And if we think of methane, CH4, that's a carbon hydrogen compound that is a gas, right? It's a really common gas. Silane is SiH4. Silane is just sort of the silicon analog of methane. So what we can guess reasonably is that silane is formed, and we can guess that it's a gas. Why? Because methane is a gas. So maybe silane is a gas. And silane would be incredibly reactive, or very reactive. Why? Because silicon likes to be, in our AP Chem, we always thought about silicon in network covalent solids, right? We thought of silicon in SiO2 in these sort of like giant tetrahedral frameworks where every atom was connected to every other atom, right? We had basically tetrahedra of silicon and oxygen, and it was this continuous molecular thing, not these distinct molecules. And so we can think that, okay, maybe this makes sense. We form silane, and then this, because it was in the first experiment, right, in our first thing, we said that no gas was collected, maybe because the silane reacted. But then when we had an inert atmosphere, our silane didn't react, and we could collect the gas. So that makes sense, right? And then when the gas was introduced to a balloon with oxygen, so when silane was introduced with oxygen, we had the volume decrease. So maybe the silane was reacting with the oxygen to form something else. So we can sort of think on this track, and it makes a little bit of sense. So let's write silane. And now let's balance the expression and see if we can get a actual reasonable equation, right? So let's first balance the magnesiums. We have 2 magnesiums on the left side. Let's add 2 magnesiums on the right side. We have 4 chlorines on the right side, so we need 4 chlorines on the left side. And now we have 4 hydrogens on both the left and right. and one silicon on both the left and right. So we have a balanced expression. So here is our expression. Here's our chemical equation. And the identity of our gas is silane, SiH4. And what exactly was our reasoning, right? We had a bunch of reasoning sort of things. We said that, okay, we know magnesium reacts to form our MgCl2. That's what we knew from magnesium reacting with acid, hydrochloric acid. And we know that silicon and hydrogen need to form some sort of compound because these are the only two that weren't accounted for in the reaction. We know that there was no hydrogen gas production, so our hydrogen gas needed to be accounted for. Our hydrogen atoms needed to be accounted for in our silicon-hydrogen molecule. We knew that both Mg and Si reacted because there was no residue, which means that silicon could not just have been left behind. We needed it in a molecule again. So these were all the sort of things that helped us guide us towards guessing, educatedly sort of thinking about silane being our gas. Now let's look at the final question, 1.8. Instead of hydrochloric acid, a mixture of dry chlorine and argon gas was allowed to react with the compound in a closed container. At high temperatures, a soluble solid residue containing X was present, but Y was not found within that solid residue. When water was sprayed inside the container, pH tests illustrated that water was acidic. Okay, so this is kind of lots of information here that we got to decipher. First thing to note is that we're reacting our compound with chlorine and argon gas, and it's dry, so there's no water, right? Okay, argon is basically non-reactive. We can sort of not think about argon. Why? Because argon's a noble gas, right? It's not going to react with anything, really. It's very, very unreactive. So let's just eliminate argon, and let's think about what happens with chlorine, because chlorine is much, much more reactive, right? Let's think about chlorine. So basically, we're reacting this compound essentially with chlorine. Okay. At high temperatures, a soluble solid residue containing X was present. If we're reacting this with chlorine, right, Mg2Si plus chlorine, we only have chlorine that can form compounds with these things, right? So what is this magnesium chlorine compound? The same exact thing we've found before, MgCl2. And it's soluble because, remember when we were reacting our compound with acid? If you remember when we were reacting our compound with acid, we had our magnesium reacting with the acid to form MgCl2 and hydrogen gas, but the only solid residue was Y, right? We know that MgCl2 is soluble because if that wasn't soluble, there would be more solid residue. Because the only solid residue we found was Y, and MgCl2 was soluble in and didn't form a solid, right? So basically, that sort of makes sense, and we can see that our soluble solid residue containing X must be MgCl2. Y was not found within that solid residue. Okay, but basically now we can sort of educatedly guess, right? The only thing that can be happening with silicon and chlorine, the only compound it really can form is silicon. We need some silicon chlorine compound, basically, to have this reaction. Because if Y was found within the solid residue, we would know that Y didn't react. If Y in solid, right? Remember when we did our acid reaction at the very, very beginning, our Y didn't react, and that's why it was in the solid residue. Because Y was not found within that solid residue, we know Y must have reacted. Y must have reacted with the chlorine, because that's the only thing there is to react with. Silicon must have reacted with the chlorine. So how can we form a silicon-chlorine compound? SiCl4. Just like carbon, silicon likes 4 bonds to give it the octet it wants, right? So this is a reasonable guess. Silicon SiCl4 as our gas or something that's being produced, right? And so let's balance this reaction, our chemical equation. And if we balance this on both sides, right, we have 2 Mgs. We have 1 silicon And on the right side, we have 4 chlorines. We have 8 chlorines total, so we need 8 chlorines total on the left side. So as you can see, we've balanced our final expression, and this is one of the reactions. But now there's another reaction we have to worry about. When water was sprayed, so remember we had a dry container. Now we're spraying water inside the container. pH tests illustrate that the water was acidic. So what does water being acidic mean, right? Water being acidic means that we have some acid that's produced. Right now there's no acid, right? Right now there is magnesium chloride, which is just a normal ionic solid that wouldn't be acidic in solution. And we have SiCl4, that's also not an acid as yet, right? So if we think about this, we need to form an acid, and one way to form an acid is maybe through reacting with the water that's sprayed in the container, right? So maybe the water was reacted with by something. Which one of these would be really unstable, right? We already talked about how silicon likes to be in network covalent solids. That's why SiH4 liked to be in a network covalent, or SiH4 was not stable, and it likes to react with the oxygen, maybe to get to a network covalent solid, right? Maybe SiCl4 does the same exact thing, because that's, again, just a molecule. It's a molecule, but silicon doesn't like molecules. Silicon likes network covalent, continuous tetrahedral structures. So this probably, the SiCl4, would be the one that's reactive. It's going to react to get to a network covalent solid. So let's look at what it could react with. It can react with the water that's sprayed in the can. So what could this do, right? We know that it must form some sort of acid. And what's an acid that we can form from hydrogens, right? Hydrogen would be the acidic part, and we have chlorines. We can form HCl. And what does that leave us with? That leaves us with, once we balance it, SiO2. So let me show you how I got here, right? So we have SiCl4, H2O, and we noted that, okay, we need an acid, right? How do we get an acid from silicon and chlorine, silicon, chlorine, hydrogen, oxygen? HCl is the most probable acid that would form. So now let's balance it. Let's balance it first. I'll take the SiO2 out, and let's sort of balance what we think. We need 4 HCl's because we have 4 chlorines and 4 chlorines. We need now 2 H2O's because we need 4 H's on both sides. And that leaves us with 1 silicon and 2 oxygens unaccounted for. So we need our SiO2. And what is SiO2? That's the most common silicon substance, basically, ever, right? This is silicon dioxide, and this is what's, in glass and what's in sand and what's in basically everything. Silicon dioxide is really, really stable. So basically the key to get out of this is that this compound, silicon dioxide, is really stable because it's network covalent, and it's got really strong bonds. It's very thermodynamically stable. So it's going to want to form silicon dioxide because that's the most stable, basically the most stable state. So now we've sort of decoded what the actual reaction is. So this was pretty cool, right? We knew that there had to be acid produced. We looked at, okay, what could possibly be the acids produced? We have hydrogen, we have chlorine, we have silicon and oxygen, probably HCl, right? Then we discovered, or say you already knew that silicon dioxide was really stable, you would immediately guess that, okay, the silicon and oxygens come together, right? And the HCl's are left behind, and that's what's the acid. That's what makes the water acidic. So if we want to look back, right, I encourage you to do this. So that was 1.8, right? Our final reaction was SiCl4 plus H2O goes to form SiO2, sorry, this should be 2H2O plus 4HCl. And if we want to go back and look at our this clue, right? We said that when we had this gas, the gas SiH4, introduced into a 1 liter balloon filled with oxygen at STP, the volume decreased by 58.4%. Why is the volume decreasing? Say we had SiH4 plus O2. We know that silicon dioxide is really, really stable. This wants to become silicon dioxide. Silicon dioxide is network covalent. Silane is just molecular. Silicon does not like molecular. Silicon likes network covalent. So this is going to form SiO2 and water, right? So let's balance this, right? Say it formed, so first of all, maybe you were thinking this forms silicon dioxide and H2. So if I balance this, right, SiO2 and 2H2, but this wouldn't make sense. Why would this not make sense, right? Because we have 2 moles of gas on the left side, 2 moles of gas on the right side, right? So what does this mean? This means that this reaction wouldn't take out a net amount of gas, right? It would just take out 2 moles of gas, but put back in 2 moles of gas. So the volume of this balloon should not decrease, because it doesn't matter what the gas is. As long as the moles are the same, the volume should be the same. So the identities of the gas don't matter. Remember that for ideal gas law. If we use up 2 moles of gas, spit out 2 moles of gas back, we know that our total volume should not change. So this cannot be the correct reaction. So let's rethink it, right? Instead, what's another thing that we could form with H2, right? All our silicon is accounted for here. What's another thing we could make with H2 or H and O? We can make water. Water is a liquid, right? Silicon dioxide is a solid. Think of glass, silicon dioxide, that's a solid. Water is a liquid, so now we're not forming any gas. And when we're not forming gas, we're just sucking the gas out. We're just reacting to form solids and liquids. That's going to reduce the volume, because now the moles of gas are decreasing, right? And when moles of gas are decreasing, that means our volume is going to decrease. So let's actually write out the exact expression for this. We have silane, SiH4, plus our oxygen, right, goes to silicon dioxide and water. And if we balance this expression, how do we balance this expression? We need to balance the H's first, right? We have 4 H's on this side, on the left side, 4 H's on the right side. That makes sense. Now we want to balance our oxygens. We have 2 oxygens, 2 in the SiO2, 2 in the H2O. So we need 4 oxygens on the left side, and so we have 2 O2. So this is our reaction. That basically, this is the reaction that's happening when we introduce our silane to the oxygen-filled balloon. The silane is reacting with the oxygen. It's taking out now, right? It's taking out 2 moles of O2, right? So for every silane you introduce, you're removing 2 moles of O2, and in total, we're removing 3 moles of gas, because we have our 1 mole of silane and 2 moles of O2, and we're removing that completely and forming solid and liquid. We're removing the gas. We're reacting to form solids and liquids, which don't contribute to the balloon's volume, right? The majority of the volume comes from gases. And so because we're just removing gas, we're going to decrease the volume of the balloon. And I encourage you, if you want to actually check that this quantitatively is correct, because we're told that it reduces by 58.4%. I won't do it in this video, but you can use ideal gas law and use this equation to check that actually the volume will decrease by 58.4%, because that just means the moles of gas decreased by 58.4%. So cool. So this was a run through of the SChO bronze problem 1. I hope that it was useful to you. It was really quite a difficult question. It really wasn't locals level, but I think it was a pretty good question to go through. It really helps you think about how to approach stoichiometric problems. I think a big takeaway is to just look at the things that you think are important, right? Look at these key facts. For example, look at the water being acidic. Look at the solid residues. Look at the fact that a soluble solid residue is formed. For example, in previous parts, like these, look at, if we go back, look at gas evolving, look at the pop tests, look at stuff like that, right? These are all really important things to look at and to think about, and take all this information and decipher it. Another really key thing to note for any stoichiometric questions is to keep these sort of variables, right? Have your variables of k, have your variable, you can call them whatever you want, but have these variables where you can systematically run through it and run through a bunch of cases. You can have case 1, k equals 1, case 2, k equals 2, etc., etc. Have these systematic ways of looking at problems, and if you have this sort of casework going on, it makes it really easy, or much easier, to run through and check all the different cases, rather than sort of guessing a compound and checking later. So I think those are two of the main takeaways I want you to get from doing this problem, and hopefully this helped you decipher this problem a little bit. I know it was quite difficult. Thank you so much for watching, and I'll see you in the next one.